Swayam Prabha. Digital India. Educated India.
Good morning. Today we move further. In lecture number 38, we discuss a new model of surface patches, namely boundary interpolating patches. Here we are going to be working with only boundary curves. So given boundary curves, interpolate between them to achieve boundary interpolating patches. This is what the idea is. One can have 2, 3 or 4 bounding curves. As you would have observed in case of Bezier patches or B-spline patches, the boundary curves in those cases are Bezier or B-spline curves themselves. So in a way, the tensor product patches and the boundary interpolating patches are interrelated. One can also have slope information at the boundary curves, or what we call cross boundary tangents. I'll tell you in a little while what I mean by them. The first model, ruled patch. So given 2 boundary curves, R1 of u and R2 of u. This is the first curve, this is the second curve, R1 of u and R2 of u. One can perform linear interpolation between 2 corresponding points on the respective curves, like so. It's like sketching or drawing different straight lines joining 2 corresponding points of these 2 curves. Mathematically, a ruled patch can be expressed as R as a function of u and v equals 1 minus v times R1 of u plus v times R2 of u. So these are the u parametric directions, while these are the v parametric directions. So if you notice, it's a linear interpolation model. We can rewrite this expression as R1 of u plus v times R2 of u minus R1 of u. This vector here gives some sense of the tangent information between the 2 curve models, R2 of u minus R1 of u. The second model, lofted patch, given again 2 boundary curves, R1 of u and R2 of u, and also given additional information pertaining to cross boundary tangents T1 of u and T2 of u. For example, these are the 2 curves, R1 of u and R2 of u, and we have these as cross boundary tangents. denoted by T1 of u and T2 of u. The directions shown here are opposite. What we can do is, for any value of u, we can choose a corresponding point on this curve, and loft a curve using these two corresponding tangents, like so. And that is the basic difference between a ruled patch model and a lofted patch model. In a ruled patch model, we simply join the corresponding points by a straight line. But here, we use a higher order curve, in this case cubic, to create the lofted effect. Mathematically, a lofted patch can be written as R of uv equals phi 0 of v r1u plus phi 1 of v r2u plus phi 2 of v t1u plus phi 3 of v t2u. R1, R2, T1 and T2 are given to us. Any guess as to what phi 0, phi 1, phi 2 and phi 3, all as functions of v, can be? You are right. These are the Hermite polynomials, the Hermite cubic polynomials that we had seen in case of Ferguson segments. The next model, bilinear Kuhn's patch. Given 4 boundary curves. In all the previous models, we had considered 2 boundary curves, and in the lofted patch, we had also considered cross boundary tangents at those 2 curves. But here, we work with 4 boundary curves. Of those, this is the first one, this is the second one. This boundary curve here is denoted by b sub 0 function of u, b sub 1 function of u. We have 2 more. These are denoted by a sub 0 as v and a sub 1 as a function of v. This is the u parametric direction, and that is the v parametric direction. There will be 4 points of intersection. The first one is represented as P00. This would correspond for values of u and v both as 0. This is P10 for u equals 1 and v equals 0. P11 for u and v equals 1, and P01 for u equals 0 and v equals 1. Here, we do not have any additional information, so we'll probably be using ruled surface models. We can obtain them by combining any 2 pairs of opposite curves. For example, we can combine these 2 curves or combine these 2 curves. Let's say the first ruled patch model, R1 of uv, is given by a linear combination of b0u and b1u. This model and this curve model, 1 minus v times b0u plus v times v1 of u. Likewise, we can have another ruled patch, R2 uv equals 1 minus u times a0v plus u times A1 V. Once again, we have a ruled patch by combining these two models, and we have another ruled patch R2 by combining these two opposite curves. The Kuhn's bilinear patch can be obtained by adding R1 and R2. R UV equals R1 UV plus R2 UV. But wait a minute. Why are we subtracting R3 UV? We don't know anything about it. We'll probably have to make this adjustment to make sure that all the boundary conditions are met. So R3 of U and V is like a correction surface to ensure the boundary conditions are properly addressed. We need to determine R3, and we'll do this next. So the correction surface, how do we determine this? So this is the previous picture of bilinear Kuhn's patch. I have copied the expressions for R1 here and R2 here. Now let's take a look at some of the boundary conditions to determine R3. Remember that R is R1 plus R2 minus R3. Now RU 0 is what? Corresponding to values of V equals 0, RU0 is the curve B0U, which is equal to R1 U0 plus R2 U0 minus R3 U0 from the Kuhn's patch model itself. Now look at what R1 U0 can be. If you plug in V equals 0 here, this expression will be 0, and this will simply be B sub 0 of U. So R1 U0 is B0 of U plus 1 minus U A0 0 plus U A1 0. These two terms come from here. If you plug in V equals 0, we have 1 minus U A0 0 plus U A1 0 minus R3 of U and 0. If you look at A0 of 0, we are here on this curve, and for value V equals 0, we are here on this point P sub 0 0, which is what this is. Likewise, if you look at A1 of 0, we are on this curve, and for V equals 0, we are on this point P10, which is this here. So if we consider the right hand side and the left hand side, B0 of U would cancel out, and eventually we'll have R3 U0 equals 1 minus U P00 plus U times P10. Let's save this result. Let's proceed further. Bilinear Kuhn's patch. We are now looking at R U1. RU1 will be R1 U1 plus R2 U1 minus R3 U1. For value of V equals 1, what is the surface? RU1. This is this curve here, this bounding curve, V1 of U. Now plug in the value of V equals 1 here and V equals 1 here. What do you get? For V equals 1, we get V1 of U from R1 UV, and for V equals 1, we get A0 1, A1 1 from R2 UV. So the right hand side can be solved as V1 of U plus 1 minus U times A0 of 1 plus U A1 of 1 minus R3 U1. Look at what A0 for V equals 1 is. We are on this curve. For V equals 1, we are at point P01, which is this. What is A1 for V equals 1? We are here. For V equals 1, we are at point P11. With this right hand side, with this as the left hand side, V1 of U cancels out, and so we have R3 U1 equals 1 minus U times P01 plus U times P11. Okay, so where are we heading? Let's copy the two results from before, one corresponding to R3 of UN1, which is equal to 1 minus U times P01 plus U times P11, and the second corresponding to R3 U0, which is equal to 1 minus U times P00 plus U times P10. What can we do with these two results? Well, we can linearly blend them in this manner. So we can linearly blend R3 U0 and R3 U1 to get R3 UV. That is, R3 of UV equals 1 minus V times R3 U0 plus V times R3 U1, where R3 U0 is this here and R3 U1 is this here. That is equal to 1 minus V times 1 minus U times P00 plus U times 1 minus V times P10 plus 1 minus U V P01 plus UV P11. If you work your algebra properly, you will notice that if you use R3 UV in this form, R UV, which was the original model for this bilinear Kunz patch, which was the sum of R1 UV, linear blend between B0 and B1, R2 UV, which was the linear blend between A0 and A1, and if you subtract R3 UV from that sum, R3 UV is given by this expression, you would realize that all your boundary conditions are met. What are your boundary conditions? These are your 4 corner points, and these 4 are corresponding bounding curves. In matrix form or in short form, the bilinear Kunz patch is given by the row vector 1 minus uu times a0 of v, a1 of v arranged in column form, plus again a row vector involving parameter v, which is 1 minus v, times the column b0 of u, b1 of u, which are these two bounding curves, minus your correction surface, which is 1 minus u times p00, p01, p10, and p11 times the column vector 1 minus v. So this is the mathematical expression for your bilinear Kunz patch. In a similar manner, can you think about creating a bicubic Kunz patch with these four bounding curves, and to loft these curves you would need cross boundary tangent information. Once again, with these four bounding curves and with the respective cross boundary tangent information, is it possible for us to create a bicubic Kunz patch? We will see this now. Let me warn you beforehand that although the principle is relatively simpler, the mathematical expressions involved are intricate. I would like you to pay full attention to the following discussion. So given 4 bounding curves and 4 cross boundary tangents. So these are 2 of the 4 curves, b0 of u and b1 of u. These are the other 2, a0 of v and a1 of v. For b0 of u, we have the tangents as t0 of u, and for b1 of u, we have the tangents as t1 of u. What would these cross boundary tangents mean? Well, physically, if you stand at any of these points, t0 of u would be a set of directions which would be tangents along the v parameter direction. Likewise, t1 of u will be the tangents if you stand on any of these points on b1 of u. Again, these would be the directions along the parameter v direction. Likewise, the other 2 sets of cross boundary tangents, s0 of v and s1 of v, will be pointing along the parameter u direction, like so. Okay, recall now what we did when we created a lofted patch. For a given u, we chose a point, we chose the corresponding tangent direction. For the same value of u, we chose a point here on this curve, b1 of u. Correspondingly, we also had the tangent information, and we lofted a curve along the v direction. We are going to be doing something very similar here. As we did in case of bilinear Kunz patch, we will create 2 lofted surfaces, R1 of UV and R2 of UV, and we'll subtract a correction surface from this sum. So these are the two parameter directions, U and V. As you would know, these are the four corner points, P00, P10, P01, and P11. As I mentioned before, we'll follow a very similar procedure as in the bilinear Kunz patch to blend two bounding curves, B0 of u and B1 of u, using cross boundary tangents T0 of u and T1 of u, to get R1 of uv equals phi 0 of v times B0 of u plus phi 1 of v times B1 of u plus phi 2 of v times T0 of u plus phi 3 of v times T1 of u. Phi 0, phi 1, phi 2 and phi 3, as you would realize, are Hermite cubic polynomials in V. Likewise, we are going to be blending the two other bounding curves, A0 of V and A1 of V, and we'll use cross boundary tangents S0 of V and S1 of V. And this way we'll create the other lofted patch model. R2 of U and V is equal to phi 0 now is going to be a function of U times A0V plus phi 1 of U times A1V plus phi 2 of u times S0V plus phi 3 of u times S1V. So our bicubic Kunz patch is given by R of u and v is equal to R1 of uv plus R2 of uv minus the correction surface, as in the case of bilinear Kunz patch, which is R3 of uv. Once again, we will determine this correction surface to meet all the requisite boundary conditions. Let's continue. So I have copied the expressions for R1 uv here and R2 uv here. We'll need these expressions to compute the correction surface R3 of u and v. So this is the information that we have, the four bounding curves and the four sets of cross boundary tangents. Now let's compute what RU0 is. Plug in the value of V equals 0 here and here. So we have phi 0 of 0 times B0u plus phi 1 of 0 times B1 of u plus phi 2 of 0 times T0 of u plus phi 3 of 0 times T1 of u plus phi 0 of u A0 0 plus phi 1 of u A1 0 plus phi 2 of u S0 0 plus phi 3 of u S1 0. And of course, we are subtracting the correction surface R3 u and now V equals 0. As I mentioned, the expressions will be quite intricate. And what is our u for v equals 0? This is this bounding curve, b0 of u. Okay, let's analyze this a little further. If you remember your Hermite cubic functions, you would notice that phi 0 of 0 is 1, and all the other three will be 0. What's next? Look at a 0 of 0. Here on this curve, for v equals 0, we have point p 0, 0. How about a 1, 0? We are on this curve here. For v equals 0, we are standing on p1, 0. How about s0 of 0 and s1 of 0? You're looking at the cross boundary tangents s0 of v. For v equals 0, the cross boundary tangent along the u direction will be defined at p 0, 0. S1, 0. You're looking at these sets of cross boundary tangents, and for v equals 0, S1 of 0 will be defined at p1 of 0. We'll come to these later. For now, if we solve this equation, we have our 3u of 0 equals phi 0 of u times p0, 0 plus phi 1 of u times p1, 0 plus phi 2 of u times s0, 0 and phi 3 of u times s1, 0. If you notice, this term here cancels out with this term, and we have taken this term on the right hand side here. Okay, let's proceed. So we have this patch, and now we are interested in finding what our u1 is. All we need to do is we need to plug in value of v equals 1 here, here, and we need to subtract our 3u1 from the sum. So the sum is phi 0 of 1 times b0 of u plus phi 1 of 1, b1 of u plus phi 2 of 1, t0 u plus phi 3 of 1, t1 u. Plug in v equals 1 in this expression to get this expression. Okay, plug in v equals 1 here to get this expression, which is phi 0 of u, a01, plus phi 1 of u, a11, plus phi 2 of u, s01, plus phi 3 of u, s11. And of course, we have minus r3 u1. And after all, what is r of u and 1? This is for v equals 1. We'll have this bounding curve here, b1 of u. Once again, if you remember the expressions for your Hermite cubic functions, this term goes to 0, this term goes to 1, this goes to 0, and this goes to 0. We can simplify this complex looking equation as r3 u1 equals phi 0 of u times p01 plus phi 1 of u times p11 plus phi 2 of u s01 plus phi 3 of u s11. Look at this expression here. Where did this come from? a01. Beyond this curve, put v equals 1 to get P01. Once again, A11. Beyond this curve, put V equals 1 to get P11. These are the cross boundary tangents at V equals 1. Here and here for this one. Do you have an inkling as to what we are trying to do here? In the previous slide, we computed R3 U0. Here, we compute R3 U1. And if you notice, R1 of UV and R2 of UV were two lofted patches that were created using the bounding curves and the cross boundary tangents. We are trying to do something very similar here to find R3. Let's see what's in store for us next. So here I have copied the 4 important results that we would need. R1 of UV, R2 of UV, R3 of UN0, R3 of UN1. You must have noted down these expressions in your notes. All we would want to do now is to think about creating a lofted patch to get R3. And for that, we would need information pertaining to the first partial derivative of R with respect to V. So partial R over partial V is partial R1 over partial V plus partial R2 over partial V minus partial R3 over partial V. So this unfolds the suspense. If you plug in value for V as 0 and 1 respectively, we will have first derivative information of R3 with respect to V. So with these two information and with these two, we can think of creating a lofted patch for R3. So partial R over partial V will be equal to partial of this expression with respect to V plus partial of R2 with respect to V minus partial of R3 with respect to V. Okay, so the first expression is partial of phi 0 with respect to V times B0U plus partial of phi 1 with V times B1U plus partial of phi 2 with V times T0U plus partial of phi 3 with V times T1 of U plus phi 0U times partial of A0V over partial V plus phi 1U times partial of A1V over partial V plus phi 2U times partial of S0V over partial V plus phi 3U times partial of S1V over partial V minus partial of R3 over partial V, which is this term here. Once again, you can compute the first derivatives with respect to V through these expressions here. Let's now define twist vectors denoted by chi sub I j, which is equal to the mixed derivative of R u v with respect to u and v. evaluated at u equals I and v equals j. I and j would go from 0 to 1. These mixed derivatives are equal to partial SIV over partial v, which are also equal to partial TJU over partial u. As I said before, I can assume any value 0 or 1, and so is the case with j. We'll need these expressions R3 of u0 and R3 of u1. So I have copied these equations right here. Now for value v equals 0, partial a0 of 0 with respect to v. So in a sense what we are doing is we are computing partial of a0v with respect to v and evaluating that at v equals 0, and that will be equal to t sub 0 evaluated at 0. Likewise, partial of a1v over partial v, where v equals 0 is equal to t sub 0 evaluated at 1. This is our balloons patch. This vector here would correspond to t sub 0 evaluated at u equals 0. Likewise, this vector here will be equal to t0 for u equals 1. Partial of r over partial v for v equals 0 is equal to t0u plus phi 0u t0 at 0 plus phi 1u times t0 at 1 plus phi 2u times chi 0 0 plus phi 3u times chi 1 0 minus partial r3 with respect to v evaluated at u equals u and v equals 0, and that is equal to t0 of u. For v equals 1, partial of a1 with respect to v for v equals 0 is equal to t1 of 0, and partial of a1 with respect to v for v equals 1 is t1 evaluated at 1. These two vectors are given by these red arrows. t1 at u equals 0 and t1 at u equals 1. So we'll have partial of r with v for u and v equals 1 is equal to t1 of u plus phi 0 u t1 at 0 plus phi 1 u t1 at 1 plus phi 2 u times chi 0 1 plus phi 3 u times chi 1 1 minus partial of r3 with v for u equals u and v equals 1, and that will be equal to t1 at u. So from this equation we can compute partial r3 with respect to v at u and 0, and from this equation we can compute partial of r3 with v at u and 1. And we already have information pertaining to r3 for u and 0 and r3 for u and 1. All we need to do is use the set of 4 data to create a lofted surface R3. To summarize, R3 of U10 is phi 0u P00 plus phi 1u P10 plus phi 2u S00 plus phi 3u S10. R3 at u and v equals 1 is equal to phi 0u P01 plus phi 1u P11 plus phi 2u S01 plus phi 3u S11. And just about now we had computed what partial R3 over partial V are for V equals 0 and V equals 1. They are respectively phi 0u T00 plus phi 1u T01 plus phi 2u chi 00 plus phi 3u chi 10 and phi 0u T10 plus phi 1 of u T1 evaluated at 1 plus phi 2u chi 01 plus phi 3u chi 11. For the correction surface R3 u v, this is the information we have. R3 u0, R3 u1, partial R3 over partial V at u and 0, and partial R3 over partial V at u and 1. With this information, it's very natural for us to create a lofted surface R3 uv as phi 0, now a function of v, times R3 u0 plus phi 1 function of v times R3 u1 plus phi 2 function of v times partial R3 over partial v u0 plus phi 3 v times partial R3 over partial v u1. These are the expressions we'll have as functions of u, and phi 0, phi 1, phi 2 and phi 3 will be Hermite polynomials in V. You can do the math and verify that R3 uv constructed in this manner would satisfy all the boundary conditions pertaining to the corner points, pertaining to the bounding curves, and also relating to the cross boundary tangents. By this time, you would already have the expression for R3 u0, R3 u1, the slope with respect to V evaluated as u0 of R3, and the slope with respect to V of R3 evaluated at u1.